Hello, I'm Perrine Chassa and I'm presenting at this conference a collaborative work with Julian Park and Nicolas Brunel. So our research focuses on shape analysis of Euclidean curves within the framework defined by the Frenet-Serret formulas. So therefore, the central problem we aim to address in this work is what is the best, or at least the most suitable method for comparing shape of a set of Euclidean curves in arbitrary dimensions, independently of any shape-preserving transformation, such as translation, rotation, reparametrization, or scaling. So the general approach for defining the shape analysis method is to find a good mathematical representation of a Euclidean curve that exhibits invariance property to these rigid transformations, but also provides Riemannian manifold structure that is known to offer powerful tools for studying the geometry of curve and the statistical properties. So therefore, the primary challenge in shape analysis lies in the choice of this mathematical representation. And in particular, the Frenet-Serret formulas define mathematical objects that fully and uniquely characterize the geometry of a Euclidean curve. A bit more specifically, the Frenet-Serret differential equation is defined in the rotation group SOD and is parameterized by the Frenet curvature function and has a unique solution called the Frenet path that uniquely defines the shape of the curve and its complete geometry. But however, we have observed that the classical approach used in shape analysis, that is based on the SRVF representation, that is square root velocity function, implicitly uses only part of this geometric information. So in this work, we propose two alternative representations of Euclidean curves that leverage their complete geometries through the Frenet curvature function. And in addition, we provide the development of their associated Riemannian frameworks, and like the SRVF representation, our approaches also yield to explicit formulas for geodesics and geodesic distances. So the first representation that we have considered is based directly on the unparameterized Frenet curvatures, but we demonstrate through experiments that it defines a shape analysis framework that lacks elasticity. So as a main contribution, we propose a second representation of a Euclidean curve that we call the square root curvature transform, and that is inspired by the square root velocity transform of the SOD valued Frenet path. And so since this representation depends on the parametrization, it involves a registration problem that imparts elastic properties through the representation. So finally, to assess and to compare these metrics, we consider a consistent set of curves that are characterized by specific features, such as ellipses in 3D characterized by having constant curvatures, or loops in 2D characterized by having a single peak of curvature between 0 and 1. And we demonstrate that only the square root curvature transform defines a shape analysis framework that remains consistent within each of these sets. And in addition, in the paper, we also demonstrate the interest of this Frenet-based representation within with a real-world application, that is the analysis of human motion trajectories. So thank you, and please feel free to visit our poster and to attend our presentation at the conference.